All right, so today we will continue the same paper 6-2 of October number 2025. Continuing from question number 2. A student investigates the reaction between the acidic solution B and two different solutions of aqueous sodium hydroxide, which are solution C and solution D, using two different indicators. The student does two experiments. Experiment 1, you can read through these lines by yourself. Drain the burette with distilled water, then with solution C, fill the burette with solution C, run some solution out of burette so that level solution is on burette scale. Just read through these lines by yourself. We move on to the question. Question number A says, use the burette diagrams in figure 2.1 and 2.2 to record the readings for experiment 1 and experiment 2 in table 2.1. Complete the table. So we have these readings and we have to measure the readings, note the readings in the table given below. So just like in the previous cases we used to do it, we will do the same again. For experiment 1, the experiment 1 is done with the solution C or the sodium hydroxide. So burette reading at first endpoint. There are three types of the diagrams, one with the initial burette reading, the other one belongs to first endpoint, and the third diagram belongs to second endpoint. So for experiment 1, using solution C, we have the value. If you can see, it is 1. This will become 1.1, 1.5, and this is 1.6. So I will write the values in front of it so that it can be easier to note down the values in the table. This is 1.6. This one is 21.2. This one is 41.0. And this one is 0.4. This one is 10.2. And this is 20.1. Now write down the values here. Burette reading at first endpoint of experiment 1. First endpoint, this is first endpoint. So first endpoint is 21.2. Okay, I have the values in my side. So 21.2 for experiment 1, and for experiment 2, first endpoint. For experiment 2, it is 10.2. Then burette reading at second endpoint. So these third diagram belong to second endpoint. So for experiment 1, it is 41.0. For experiment 2, it is 20.1. And initial burette reading. So for first case, it is 1.6. For second case, it is 0.4. Now, volume added from the burette to reach the first endpoint. You have to find the volume added, that is volume required, which is basically the difference between the initial value and the burette reading at the first endpoint. So you will take the difference of these two values to find the volume added to reach first endpoint. It is 21.2 minus 1.6. It is equal to 19.6. Now do the same for the second case. So we have 10.2 minus 0.4. 10.2 minus 0.4 is equal to 9.8. Then total volume added from burette to reach second endpoint. So second endpoint is this one. Now you will take the difference of the initial value, initial burette reading, and the burette reading at second endpoint, which means it will now be 41.0 minus 1.6. It is equivalent to 39.4. And then the second case, it is 20.1 minus 0.4. It is 19.7. You don't need to write the subtraction. These digits, I have done this just to show you the working. You do not need to do this. All right, now next part is explain why the conical flask is rinsed with distilled water at the start of experiment 2. The experiment 2 was supposed to be done using solution D instead of the solution C. Now C and D, you already have the workbooks with you. You can read by yourself as well. Solution C and D both are sodium hydroxide, and they are being reacted with the solution B, which is acidic. This one is acidic. But definitely there will be a difference of solution C and D. That's why they have to rinse the conical flask, which was previously containing the solution C. Now, why are we rinsing with the distilled water to use in the second experiment? It's a clear thing that there would be definitely some contaminants, some impurities left behind in the conical flask. So that's why we rinse to clean that. So you write here, you can say to remove impurities or to clean it. That's why you are rinsing with the distilled water. Then next part, at the start of experiment 1, the burette is rinsed with distilled water and then with the solution C. Explain how the volume added from the burette to reach the first endpoint would be different if the burette was not rinsed with the solution C. If we go back to the procedure of the experiment, this is called procedure in which the steps are mentioned. So according to this, we see that the burette is rinsed with the solution C before carrying out the titration reaction. We can see here in the first point, rinse the burette with distilled water. First, you will rinse the burette with distilled water, then discard it, and then pour the solution C into the burette. And then you can do the titration reaction. So if we do not follow this, if we do not rinse with the solution C, like when you rinse the burette with distilled water and then with this solution C, you again discard it. This is the second time you discard it. For the first time you discard the distilled water, and the second time you discard with the solution C. And that's why in the next step you fill the burette properly with the solution C. Now this time you do not discard it because this time you will use it for the experiment. But in the previous case, you were rinsing with the solution C. Now, why are we doing this? Why are we rinsing with the solution C? Basically, if I draw a rough diagram of the burette part or section of the burette, let's suppose this is a part of the burette. Initially, if you had added the water to rinse it, then there will be some droplets present on the walls of the burette. If this is a part of a burette, then some water droplets, H2O droplets, will be there in the burette. So what happens uh, if you do not do this? If you do not rinse with a solution C, then as a result, you will require more amount of the solution C for the reaction, because the H2O was also there in the burette that was dissolved in the solution C. If you do not rinse it, then solution C was directly used in the burette. It is also there. I will change the color of the solution C. Let's suppose solution C is blue in color. So this blue solution C is also present along with the water droplets. So in this case, you have basically diluted the solution C, diluted it. If you did not remove the water by rinsing with the solution C, you have basically added water with the solution C. So solution plus H2O both are there in the burette, although very small in quantity, but still they are there in the burette. So to remove that water droplets, we put some amount of solution C into the burette, properly shake it, stir it like upside down. You tilt the burette upside down repeatedly so that the water droplets are thoroughly mixed into the solution C, and then you discard it. This is called rinsing. So in this way, there is now no more water droplets left behind, and there is just droplets of solution C on the walls of the burette. Now they are just solution C droplets, no H2O. No H2O droplets. Now this time, if you perform the experiment, you will get the exact volume of solution C used in the titration. So this is the reason why we do the rinsing. Now we have to answer the question. How the volume added from the burette to reach the first endpoint would be different. So if you have not rinsed with the solution C, then definitely there will be larger or greater volume of solution C used. Where used? In the endpoint, in the first endpoint. Because some water, because some water was left behind to dilute the solution C. So solution C was diluted because of the presence of the water. And if you remember, dilution has a relation with the concentration. If you remember this formula, N is equal to C into V. So C is concentration, V is volume, and they are interrelated with each other. If I say C is equal to N over V, so V stands for volume, C stands for concentration. If the volume has been increased, then concentration will decrease. And that's what called diluted form of the compound. If the concentration is less, it is diluted or less concentrated. If there is more volume, it means less concentration or less concentrated. Then, next part, explain why the conical flask is placed on a white tile during the titration. So we have already attempted this kind of a question before. The purpose of placing the burette on a white tile is just to see a clear color change. You can understand that if, let's suppose, this is a conical flask and it is placed on a white tile like this. So any color change that is occurring inside of this conical flask will be easily visible to the human eyes, since the color of the tile on which this conical flask is placed is white in color. So it is best way to clearly see the color change. So you will write color change can be easily seen. Then C part, compare the concentration of solution C used in experiment 1 with the concentration of solution D used in experiment 2. Explain your answer. Now, we have to do the comparison of the concentrations of experiment 1 and experiment 2. Over here, this is the volume which we calculated for first endpoint versus first endpoint of both experiment 1 and experiment 2. It is just stating that compare the concentration of the solution D and C. Solution C was used in 1 and solution D was used in experiment 2. So we can basically compare either these two results with each other, or you can compare these two results with each other. It's up to your choice. So I'm gonna choose the first value of first endpoint. So you can see the solution C is used by 19.6 cm cube and solution D is used by 9.8 cm cube. In other words, if you again use this relationship Cn is equal to C into V, or C is equal to N over V, C is equal to N over V, volume is inversely proportional to concentration. If the volume is increased, it means the concentration has decreased. Now, compare how much is the difference between these two. If you can simply do the calculation, 9.8 times 2 is equal to 19.6. So this is exactly 2 times of the volume. So C solution was used by 2 more times or twice the time as compared to the volume of D solution. In other words, we can say that the concentration of the solution C, concentration of solution C is half of solution D. This is half of solution D. Just by doing the calculation, you can also do the calculation for the volume of C and D done in the second endpoint, 39.4 versus 19.7. So if you check from the calculator, 19.7 times 2 will give you 39.4. So again, same results. We have used more volume of the solution C in experiment 1, and that means it has half concentration as compared to the solution D. So this is what you will write here. You can write D simply write D. You do not need to write whole word solution. D is more concentrated, or is twice concentrated than C. Why? Because a smaller volume of D is used in experiment uh, 2 and experiment 2. And experiment 2, and also you can write your answer in terms of the calculation, that is either use these values 19.6 or 19.6 and 9.8. You can write 9.8 times 2 is equal to 19.6. This belongs to D, this belongs to C, centimeter cube, and this one also centimeter cube. So this will give you complete 3 marks for the question. You need to write everything over here. You have to do the comparison. So comparison must be done quantitatively. This calculation must be there to justify your point why you are saying it is twice concentrated. I hope it's clear to everyone. Then we have D part 1. Deduce the volume of solution required to reach the first endpoint of if experiment 1 is repeated using 50 cm cube of solution instead of 25 cm cube. Alright, so solution C was required in experiment 1, and for the first endpoint to achieve, what was the volume required for experiment 1 with C? It was, this is first endpoint, and the volume used was 19.6 cm cube. Now this 19.6 cm cube was calculated when we used 25 cm cube of the solution B. 25 cm cube of the solution B was used. But in our question, we are supposed to use 50 cm cube of the solution B. So that means you have doubled it. So if you have doubled the volume of the solution B, it means it will also require double the volume of the solution C. So if you are doubling the volume of B, it means you have to do doubling of the volume of solution C. If it is 50 cm cube for solution B, then for this case, volume of solution C used in the endpoint would also be 2 times of this value, 19.6. So 19.6 times 2 will give you 39.2. This is the value, and if you look at the blank, it says volume of solution C. So it's just not the number, you have to indicate the unit of the volume as well. Only then you will get full marks. So 39.2 cm cube, because it has a unit of cm cube. The next part state why using 50 cm cube solution B would cause a problem when finding the volume of solution C needed to reach the second endpoint in experiment 1. Now we have to consider the second endpoint by the same value, 50 cm cube of solution B, which means you have already doubled the value of volume of B. Now how much volume of C will be required in the second endpoint? So in the second endpoint, we required 39.4. 39.4 cm cube was required for the second endpoint in the experiment 1 using the solution C. Okay, if you are doubling the volume of the solution B, 2 times of the volume of solution B, it means you have to do 2 times of the volume of solution C, but in second experiment, sorry, in second endpoint, which means this value, which is 39.4, it has to be multiplied with 2. So 2 times of 39.4 will give you 78.8 cm cube. Now, what's the problem with this value? This is what we have to answer. Why this value, you can say why this value would cause a problem when finding the volume. So why we have a problem with finding this value? Now, if you can remember, we are actually finding the value of the solution C, and the solution C was used in the Burette. You see, these Burette readings were giving you the readings of the solution C and solution D. Now, if you recall the capacities, of the Burettes, the Burette's capacities were used as 50 cm cube. We mostly use Burettes of the 50 cm cube in the laboratories. However, we are supposed to use Burettes of this limit, but this value is more than 50 cm cube. So this is the problem over here. This is the problem, that the Burette capacity is lower than this value. So we can say, we would say the calculated volume of B is more than the Burette can hold, since as Burette capacity is 50 cm cube. I hope it's clear. Then E part, a student repeat experiment 2. The student warm solution B in the conical flask before carrying out the titration. State the effect, if any, on the volume solution D required to reach the second endpoint in experiment 2. Explain your answer and effect on the volume solution D. Okay, the student repeated the experiment 2, but this time it warmed the solution, which means it has heated the solution in the conical flask. The sodium hydroxide was placed inside the not the it was the acid. The acid was placed. B was the acid was placed inside the conical flask. But if the student warms the solution, you might be thinking that increasing the temperature basically increases the volume. If that's what your is your answer, or your logic, be mindful that this thing happens and it's more significant in case of the gases. In gases, this point is valid, that if you increase the volume, if you increase the temperature, it will significantly increase the volume, but not in liquids, because in liquids the particles are already very particles are closer to each other, close enough. They are close enough. So increasing the temperature would not have significant effect on the volume. So you will say no change in the volume. Why? Why there will be no change in the volume? Because changing the temperature does not change the concentration or volume. There is no change in the concentration and volume, so that's why there is no change in the volume of the solution D. I have explained why, because the particles are already closer in case of the liquid phase of matter. Then we have F. State one change, the apparatus will to the apparatus that will improve the accuracy of the results. So if we go back to the state procedure of the experiment, we were using the measuring cylinder over here. Measuring cylinder was used to measure 25 cm cube of the solution B. So we remember measuring cylinder has the least accuracy. So the only improvement we can make is just use a volumetric pipette, because volumetric pipette can also help you to measure 25 cm cube of the solution instead of saying Burette, since 25 cm cube is the value which pipettes can easily measure. So use volumetric pipette. The next question 3. A student tests two solids, solid E and solid F. Test on solid E. Solid E is ammonium sulfate. Record the expected observations. The student dissolves solid E in distilled water to form solution E. The student divides the solution E into three approximate equal proportions. To the first portion of solution E, the student adds 2 cm cube of aqueous sodium hydroxide. The student warms the mixture gently and tests any gas produced. Observation. Okay, so the student has used sodium hydroxide with the ammonium sulfate. Now, by warming, the gas is produced. What will be the observation for this gas? Basically, they have definitely stated the gas is produced. We have to give observations of the gas. So if we look at the qualitative notes here, we have the ammonium ion, and the reaction is done with the aqueous sodium hydroxide. They said the gas was produced, and in the observation we see this is the ammonia gas already mentioned. Ammonia gas is produced, but we have to tell the observation. What are the observations by which you can tell this is the ammonia gas? The observation of the ammonia gas is present here. It basically turns damp red litmus paper blue. This is the observation of that gas. You do not say ammonia in the answer, you will rather say the observation of that gas, because you are performing these tests to identify the gas. So coming back to here, you will write turns red litmus paper blue. And identify the gas, it's ammonia. B part, to the second portion of solution E, the student adds about 1 cm cube of the dilute nitric acid followed by the few drops of aqueous barium nitrate. Give observations. So the compound in our subject is ammonium sulfate, and if you remember, ammonium sulfate is NH4 twice and SO4. This is the formula of ammonium sulfate. Now, if you are doing the reaction of ammonium sulfate with the few drops of barium nitrate, BaNO3 twice, you are basically going to produce barium sulfate, BaSO4. And we have repeatedly said barium sulfate has the observations of forming white PPT. So white PPT will be produced here, and it's also there in the qualitative notes. We have the ammonium sulfate, and sulfate is over here. And when sulfate is tested with the barium nitrate, you get this observation white PPT. So white PPT is formed here. Then C part. To the third portion of solution E, the student adds a few drops of acidified aqueous potassium magnate. What are the observations? So the compound is ammonium sulfate having the sulfate ion along with the ammonium ion. These two ions are present in our solution E. We have to check which of these two ions is providing you the results with the acidified aqueous potassium magnate. Now, going to the qualitative notes, you can see in front of the sulfate ion, there's nothing about the potassium magnate. KMnO4 reaction with sulfate ion is not there. In fact, not even in the ammonium ion. There is nothing, no reaction with the potassium magnate, acidified potassium magnate is given. So although it seems quite strange here why no results with these two ions are mentioned, then in this case we need to understand it more critically. In if you look in this case sulfite, there is this mentioning of the acidified potassium magnate. So it's not the sulfate, it's basically the sulfide which is giving the test with the aqueous potassium magnate and along with the uh, along with the result of the color changing from purple to colorless. Now this is the color change when it is done with the potassium magnate. One thing more, if you go to the table of the gases, you can find in front of the SO2, it is also a same test. Turns acidified at aqueous potassium magnate from purple to colorless. Now here you will do this critically. You will give the answer critically, that is. And one thing that you must understand, which is SO2 gas is basically produced by both of these ions, sulfate ion as well as sulfide ion. Both these ions are able to produce the sulfur dioxide gas. So sulfur dioxide gas is produced when either one of these two ions are reacted with the acidified potassium magnate. Although it seems to be not logically not logical here, but that's what we can say right now because no test was mentioned against a sulfate ion. So we can relate it with the sulfide ion because both have the sulfur oxide in the form of the ion. So you will write the observation in the question, the observation. So observation will be that purple color changes to colorless. And this purple color belongs to the potassium magnate. Potassium magnate color is changed from purple to colorless. However, if you look at the mark scheme, you will see they have instead written pink in the mark scheme without mentioning of oblique between the two answers. In my opinion, it's a mistake by the examiner to mention the alternative answer, because we are following the mark scheme. Sorry, we are following the qualitative notes, and in the qualitative notes there is no mentioning of the pink color, and in the mark scheme they have mentioned pink color. So they should have used this oblique sign between the two answers, colorless or pink. So even if you write colorless, that's also correct. If you write pink, that's also that's also acceptable, because they are two shades provided by the KMNO4. When it is reacted with the compounds, it can show both colors. Actually, pink is more precisely light or fade pink. Fade pink. This is the actual color, and it is not very visible to the human eyes. So that's why we sometimes mention it to be colorless. So both answers are correct. Then the last question, test on solid F. Table 3.1 shows the test and the student observations for solid F. Test 1, carried out a flame test on the solid F, and it is a yellow flame. So if you look at the qualitative notes, you will find in the qualitative notes, yellow flame is provided by the sodium ion. Sodium ion is providing the yellow flame. So this is clear from the question. Test 2 says dissolve the remaining solid F in the distilled water. Divide the solution F into 3 portions. To the first portion of solution F, add about 1 cm³ of the dilute nitric acid followed by a few drops of the aqueous silver nitrate, and the result is yellow precipitate. So we need to look at the test of the anions from the qualitative notes. Under the section of the anions, the test with the aqueous nitrate providing the yellow PPT is over here. Yellow PPT is produced, so that shows the presence of the iodide ions. Then test 3, to the second portion of solution F, add aqueous sodium hydroxide dropouts until in excess, and the observation is white precipitate form. This is for the dropwise case, and in the excess case, it says precipitate dissolves to form a colorless solution. So the test is done with the sodium hydroxide, which means it is the test of cation. So again, look at the qualitative notes. Under the section of cations, we can find the reaction with the aqueous sodium hydroxide, in one case with dropouts and in other case with excess. So you can see white precipitate which is soluble in excess, giving a colorless solution. So aluminum ion is giving you the same result, and also zinc ion is also giving you the same result. White precipitate soluble in excess, giving a colorless solution. So both of these results are same. So it means there is aluminum ion, zinc ion. Now comes a question. Test 4. To the third portion of solution F, add ammonia, aqueous ammonia dropouts until in excess, so white precipitate form, and the precipitate dissolves in excess aqueous ammonia to form a colorless solution. Now, with the ammonia, we need to see the result with aqueous ammonia, white precipitate, but it is insoluble in excess. This is insoluble in excess. And with zinc ion, white precipitate which is soluble in excess. So this shows that the compound had the zinc ion, not the aluminum ion, because sodium hydroxide could not differentiate these two, but it did differentiate from the rest of the cations. But by performing the reaction with ammonia, it has differentiated between the aluminum ion and the zinc ion. So we had the zinc ion in the compound. D says identify the three ions in the solid F. So which three ions are present in solid F? We identified sodium ion because of the flame color, and anion was iodide ion, and the third one was the zinc plus 2 ion. So these three ions were present. Now the last question. Liquid alcohols can be burned as fuels in spirit burners. The energy given out can be used to heat a water in a boiling tube as shown. This is the picture of the boiling tube, the setup. Describe how to investigate which of the three liquid alcohols, ethanol, propanol, and butanol, heats the water in the boiling tube the fastest. You are provided with the three spirit burners, samples of the three alcohols, water, and common laboratory apparatus. So you have to check which of these three alcohols, ethanol, propanol, and butanol, uh, provides fastest heating. Fastest heating is provided by which alcohol? Now, what you can understand from here that you must have a specified or fixed volume of the alcohol used, and also a fixed volume of the water used. Now, if you have three different alcohols, you what you can check here, as you have to find the fastest, it means it is related with the speed, which is related with the time. So what you can do is that record the time. Record time in which a particular temperature of the thermometer is achieved. Let's suppose you can say if you are achieving, I would say 80 degree, because do not say boiling 100 degree, because it may, because the temperature does not increase after 100 degree. You can set, let's suppose 80 degree to check it. So one, that alcohol which gives 80 degree temperature at shortest time, in the shortest interval or shortest time, will be the fastest fastest uh, boiling or fastest heating of the liquid. We have to find the heating, not the boiling point, just the heating. You could say the alcohol which provides 80 degree temperature at the shortest time will be the one providing the fastest heating. So what you can write over here, uh, contain a fixed volume of alcohol in spirit burner. Fixed volume of alcohol must be used in the spirit burner, and along with that, you have to use measured volume of water in boiling tube. Now you are supposed to do the heating. So heating changes the temperature. So what you will do at this step, record the initial temperature of water. Now you have recorded the initial temperature. Now uh, then start heating the boiling tube and measure time for attaining a fixed or specified temperature. Because let's suppose if you are trying to achieve 80 degree, you will measure time for all the alcohols. The alcohol with shortest time to achieve temperature, specified temperature, achieve fixed temperature, we can say fixed temperature will give fastest heating. It will give fastest heating. So this is how you calculate the fastest heating of the three alcohols. So that's it. We have attempted the last question of this paper as well. If you have any questions, please let me know. Okay, so no question. So fine. We will do the next variant paper, third variant of this paper in our next class. So till then, take care and Allah Hafiz.